This video is a demonstration of the use of a web application designed to provide a concise understanding of the evidence-based policymaking logic generation mechanism. According to the latest IPCC findings, if global warming continues at its current rate, sea level rise could be 1 meter by the end of the century. Sea temperatures will also increase water vapor, causing tropical cyclones to intensify and coral reefs to bleach. In small island developing states, most socioeconomic activities are concentrated in coastal areas. And some countries, such as atoll islands, have low elevations, making them vulnerable to flooding hazards caused by external weather forces. The prototyping of the policy decision-making tool was prepared by Restec under the overall guidance of the Ministry of the Environment, Japan. The purpose of the tool is to provide support for policy decision-making in addressing inundation. The tool monitors regions under risks against inundation and provides hazard predictions for critical socioeconomic infrastructure, mainly for 22 islands in 14 small island developing states. The risk assessment is based on the simulations of existing stochastic models and on climate system scenarios. Adaptation measures for flooding in the coastal areas of islands assumed in this prototype are classified as gray for breakwaters and wave-dissipating blocks, and green for conservation and rehabilitation of reef-building corals. This is what a conventional coastal disaster prevention engineering project with gray measures looks like in the current climate. With typical gray measures, we can prevent flooding hazards in a post-warming world and protect coastal socio-economies from damage. On the other hand, concrete structures not only damage the natural environment and landscape, but may also affect the coastal fishing and tourism industries. In addition, since future climate change involves uncertainty, it is necessary to harmonize the expected disaster prevention effects with the cost, such as the height of the structure. This is what happens when a reef-building coral conservation project is carried out using green measures that are ideal in terms of natural ecological engineering to supplement disaster prevention functions. Healthy reef-building corals are said to have an upward growth potential equal to the average rate of sea level rise. If the reef-building coral is healthy enough to withstand the rise in sea temperature, the depth of the coral cover area in the reef flat, including the reef crest, is said to be constant, as the rate of coral growth and sea level rise are balanced. In other words, the wave-dissipating effect of the reef ridge on offshore waves is the same as before global warming. The increase in inundation hazard will come from sea level rise and changes in tropical cyclones. The main function of coastal disaster prevention realized by the conservation and restoration of reef-building corals with high temperature tolerance is the wave dissipation of reef ridges. Compared to conventional gray measures, the ability to protect the socioeconomy from the risk of flooding hazards is limited. However, when corals are in a healthy state, they maintain their natural regulating function of keeping the depth of the shallow sea at or below a certain level for a long time, regardless of the rise in sea level caused by global warming. It is expected that the maximum flooded area will be reduced in the future, although it will take time. Green measures generally have the potential to conserve or create new ecosystem service values. For example, the conservation of coral reefs not only protects the livelihoods of coastal fishermen and tourism industry workers, but also creates employment opportunities associated with conservation and cultivation work. In this way, the benefits that green measures can bring to islands are very significant. In order for islands to adapt to the effects of climate change, such as sea level rise, it is very important to maintain the land based on ecosystem conservation. This prototype aims to compare the costs and benefits of gray and green solutions to improve climate change adaptation. By allowing users to input these figures according to local conditions, this policy decision-making tool can simulate an appropriate benefit-cost graph for each user. The following is an example of simulation for a target hazard in a certain region. The cost of constructing a coastal protection facility is calculated by multiplying the facility length by the unit cost. The maintenance cost is calculated by multiplying the above cost by the expected number of years. The benefit amount is the difference between the damage area caused by coastal inundation without countermeasures compared with the ones with countermeasures. An example of a calculated graph is shown here. It is assumed that construction will be completed in 3 years, after which maintenance costs will be added annually. The social discount rate is assumed to be 10%. It can be seen that benefits gradually rise over the construction period, and at some point, the benefits exceed the costs. Green measures are envisioned to include the planting of high-temperature tolerant corals and water quality maintenance measures to protect the corals and to calculate the cost of such measures. The benefits of green measures include increased tourism and revenues from the fishing industry, in addition to wave dissipation by corals. The amount of this increased benefit will be cumulative from year to year. An example of a calculated graph is shown here. The rise in benefits is gradual, but the cumulative amount grows. When we compare the gray and green measures, we can see that the gray measure reaches the break-even point earlier than the green measure, but the green measure produces more present value than the gray measure. Combined measures are based on both green and gray countermeasures. Combined measures are used where the hazard is severe and more countermeasures are assumed to be necessary. The cost-benefit calculation method is the same as for the aforementioned gray and green measures. An example of a calculated graph is shown here. Comparing combined measures with gray and green measures, it can be understood that combined measures generate greater benefits than gray measures, and the break-even point comes earlier than gray and green measures. We hope that this prototype will help you to determine when green adaptation measures are more reasonable than gray adaptation measures by calculating the cost of adaptation measures based on the amount of damage that future external climate change will cause to socioeconomic infrastructure, and by considering the value of ecosystem services.